Alright, we're going to try to polish up our expertise on Euler's method, and I bet if I asked you on a scale of 1 to 10 how confident you feel, you'd probably say about an 8. We did pretty good on when we saw this one on our last test, but there's a few bumps in the road, a little bit of misconception, and my challenge to you is even if you are getting the right answers, I wonder if you really can appreciate what Euler's method is doing behind the scenes besides the mere number crunching that we're so good at. So that's our challenge today, is to take our confidence level up a few more notches and to gain a deeper appreciation for what Euler's method is actually doing while we're doing all the number crunching. So our question is, how do we solve a diffy Q if we can't actually separate the variables? Now, there's lots of other tricks that you'll learn when you get to college, but for this particular course, there's two avenues we could take. Number one is slope fields, and slope fields are a graphical approach to finding a solution to a diffy Q. So it gives us a visual image. By the time we put all that effort into creating the slope field, by the time we're done, we can take a step back and be able to visualize what the curve looks like. Now, Euler's method is just the opposite. That's more of a numerical approach to approximating a solution. And so we're just two different alternatives with similar goals in mind by the time we're done. Now, I should say that the big difference is the slope field is going to give you an image of the entire solution, whereas Euler's method is more focused on approximating one specific value within that solution. We're kind of attacking one particular point. Now, what you'll notice here with the pictures I've imported, we'll start with picture number 1 up here. Now, this is just, we have one tangent line drawn at the point where at t sub 0, and so as you follow that tangent line, it kind of diverges away from the red curve, and so you know, if I wanted to approximate this value up here, it would be quite a ways off from the actual value. So what we'd like to do is, instead of just using one tangent line, we'd like to break that same interval into smaller segments that are redirected every so often. And I think the term redirection is key here. So what we're going to do is we look at image number 2 here, is we say, all right, we're going to do a tangent line at a sub 0, but we're only going to let that tangent line extend so far before we get to a sub 1 and we stop and start all over and we recreate a new tangent line. Because what we do have is we do have a diffy Q, and that diffy Q can tell us the slope at any moment on this curve. And so as we go along here, we're just going to stop, recalculate the new slope at a sub 2, which will then produce a new tangent line, which will ride so far before we stop and start the process all over again. And the image number 3 is just another similar image where you've got the blue solution curve and the red tangent lines that are kind of sequenced together. And that's all it is a series of tangent lines joined together to approximate a solution. So we'll try to kind of put into words what I tried to explain on the last slide. And the key here is Euler's method develops a series of linear approximations, just a bunch of little line segments joined together, by using the equation of a tangent line. So here's the key. If you feel good about writing equations of tangent lines, which I think we all do, then we all certainly should feel good about Euler's method. All right. Now, the idea that within a small interval, and that's the key, we don't want these lines to run too far, we cut them off after just a short distance. The curve can be approximated by a line segment is called something very special, local linearity. And that's just kind of the idea that no matter how curvy the curve is, you can zoom in enough to the point where it starts to become and act like a straight line. And then, of course, the smaller the x interval, the better the approximation. So a lot of times, like our step size, and that's what we're really saying here, the x interval, the step size is 0.5 for us generally, but there has been times where it's been 0.1, which is even more accurate and even better. Alright, just want to review how we set up our particular table. There's different ways to attack Euler's method, and we always start off with our x and our y value. And then that third column is kind of the mystery column. And basically, I want you to think point slope form of a tangent line. Alright, this is where it all started, just like this. Now we would say that y minus y sub 1 is the change in y. M is our slope, which is going to be our diffy Q, and then x minus x sub 1 is the change in x. Alright, now that change in x is, traditionally we call that our, whoops, I don't know what I'm writing, that's our step size. And a lot of times we'll use the letter h to represent step size. And then, of course, dy dx is your diffy Q, which represents the slope at any particular moment. So that's the, if you have any trouble memorizing what goes in that third column, just tell yourself, start with a tangent line and then clean it up with a little slightly different notation. It's actually the fourth column that tripped us up on the test most recently. We did a really good job with that third column, which is where most of the work gets done, but some of us, we didn't know how to interpret the fourth column. Now, I call the fourth column my new y value, okay? And basically, I'm taking my old y value and I'm adding my change in y to that to create this new y value. And then whatever number you put right here automatically gets cycled down into this slot right here to start the next row. Alright, it's time to try one live example, and this one has an interesting twist in it that we haven't seen too often. But as I set up my table here, and it's similar to slope fields where you're thinking, alright, it's a lot of number crunching and I feel like I should be able to fly through it, but sometimes we got to tap the brakes and go just a whisker slower to ensure that our accuracy is where it needs to be. Now here's the trick. We're going to start with an x value of 1, and the y coordinate happens to be 0 at that moment. Now they want us to approximate f of 0 with two equal step sizes. So I'm actually going from x equals 1 backwards to x equals 0. So my step size is going to be negative this time. And if I'm going to get there in 2 steps, each step is going to have to be negative 1/2. So I can make a note to myself up here at the top that my h value, or my step size, is negative 0.5. Okay. Let's see, so that's usually I'm going to put that part first, and you could go fractions or decimals, whichever you prefer. That should be 1/2. And then I've got my slope, which is my diffy q in this particular moment. It's 1 minus y. And then in that fourth column, that's going to be our new y value. So let's see if we can run through this. Our change in y is going to be negative 1/2 times the quantity 1 minus 0, which turns out to be negative 1/2. And if I add that value to the old y value of 0, I'll get a new y value of negative 1/2, which automatically gets recycled. Now the x value is now 1/2 because we went backwards a half, and the y value is negative 1/2. So let's see if we can plug this rascal in. We've got our negative 1/2. Then the quantity 1 minus negative 1/2. So, let's see, that's 3/2 in the parentheses. Negative 1/2 times 3/2 would be negative 3/4. If I add this to my old y value, I'm going to end up with negative 5/4. And cycle that down. So when x equals 0, our approximate y value is negative 5/4. And right there, we're done. That's our finish line right there. That's our answer. So hopefully we were able to dig a little deeper and gain a little confidence with Euler's method, and we'll really dominate it from this point forward.